Good afternoon, ladies and gentlemen. Thank you for inviting me to give this talk here on CoNGA Congress. So my title is, it goes a little bit in a different direction. Namely, what we are talking about is mainly reliability of results. So this is a very important subject in my opinion, and we should not only speak about petaflops or whatever, but also about the reliability of these results. And for these, you do not need just numbers, but also valids and quires, which were described in John Gustafson's talk before. So my outline is first a few comments about regular floating point arithmetic on IEEE arithmetic. Maybe a little bit of comparison between pure mathematics and applied mathematics. So there is a big discrepancy between these two. Some remarks on posits, and then interval arithmetic and valids. And the next step would be exact dot products, or in the language of our conference, Quires. And then some numerical algorithms with verified results and a conclusion. So first, some remarks on floating point arithmetic. I mean, everybody knows IEEE floating point arithmetic. It's nowadays more or less on all computers. In 1985, when this standard was agreed on, it was a big step forward because formerly every computer had its own arithmetic, some calculated hexadecimal, other maybe in base 2 and so on. And there were many different formats, and that was very difficult to exchange data and results. So the standard in 1985, which was later revised in 2008, made some progress in this direction. It's a widely adopted standard, and it makes the interchange of data and of programs easier, maybe not trivial, but at least a little bit easier. So on the other hand, it has many special cases. For example, these not numbers. There are lots of not numbers which can be defined in the format. It has special cases for infinities, computing with infinities, with positive and negative zeros, with gradual underflow, and so on. So there are many special cases which makes the standard a little bit difficult to handle. In fact, results are not completely identical on all computers. The results may, in fact, differ on different platforms because of subtle differences in the implementation of the standard. And in particular, results of algorithms may be unreliable. Just a little comment about pure mathematics and applied mathematics. Pure mathematics usually makes some statements like this one. For all real numbers, x, y, z, the associative law says that x plus y plus z is equal to x plus and the other sequence of operations. So that's the associative law. You all know it. But the important thing about this in pure mathematics is that we say for all. For all means for all. There is not a single exception. No exceptions are allowed in pure mathematics. That looks very different in applied mathematics or in computed results. Usually here in applied mathematics we have just an approximate solution, which may be accurate or less accurate. Usually we do not know exactly how accurate it is. Usually we have some kind of error estimation. For example, an error estimation epsilon, which somehow describes the error, but we do not rigorously know how big this epsilon is. We have maybe some approximation for it, some terms, but we neglect higher order terms and we neglect the influence of rounding error, and so this may be more or less reliable. Yeah, probably in many cases it's reliable enough or it's accurate enough, but there may be exceptions. I'll show you some examples. So what I want to underline here is that we have a big difference between pure mathematics and applied mathematics, and we should try to more or less bridge this gap between pure mathematics and reliable and applied mathematics. So let's just look at a couple of trivial examples. In floating point arithmetic, well, for example, we have here a small polynomial, p power 4 minus 4p square q square plus q power 4 for these two numbers. Actually, these numbers are integers, but you compute everything in double precision floating point arithmetic. And the result is minus 3.3 times 10 power 7. Okay, if you get this result, maybe you say, oh, okay, why not? The only problem with it is the true result is 1. So the order of magnitude is completely wrong. The sign is wrong. Every digit is wrong. So for such a trivial polynomial, it's really just power 4. This is just, I didn't count the operations, maybe a dozen floating point operations. Or maybe you can even reduce the number of floating point operations if you use p square to compute this. This is, in my opinion, really appalling to have such a large error. Another example has already been mentioned in the morning by the talk about hardware to assist Quires, the computation of matrix multiplications with Quires. Here, for example, if we have such an example, 10 power 20 plus 1 minus 10 power 20, the result is, of course, 1. But if we use regular floating point arithmetic, we get 0, because 10 power 20 plus 1, that cannot be expressed in double precision. Of course, you may say, yeah, okay, then I take extended precision, but in that case, maybe you exchange 10 power 20 by 10 power 25, and you get the same problem. Or you have a linear system. Well, I didn't write the linear system here, but it's a very simple linear system, a 2 by 2 linear system. That's really trivial. And the solution requires just 7 arithmetic operations, so it's really a very trivial mathematical problem, and all digits of the result are wrong. So, of course, this linear system is somehow very close to a singular matrix. So the two lines are multiples of each other. The second line is maybe nearly 2 times the first line. So this is not the usual case, what you expect when you're solving linear systems, but it may occur. And what I wanted to underline is that even in such a simple linear system, you may get completely wrong answers. These are a couple of graphs which I generated with 2 different kinds of arithmetic. One is double precision arithmetic, regular 53 double precision IEEE arithmetic. The other is 52-bit arithmetic. And I just simulated this by cutting off the last bit. So the 2 graphs look, well, a little bit similar, but in detail they are really different. So maybe you can choose which of these graphs is better or which is worse. The graphs in reality, they are a fractal, and I calculated the same number of steps. I used the identical coloring scheme. The only difference between the 2 graphs is the floating point format. So yeah, which of the graphs is correct, which is not correct? Well, that's maybe a matter of interpretation. Yeah, okay, of course, if we consider linear systems, 2 by 2 system, nobody would use a supercomputer for solving a 2 by 2 linear system. For example, we heard on the conference, on the SCA conference about petaflops, for example, this TNH2, which has 34 petaflops. And it's a bit complicated to imagine what this means, petaflops. So what does it mean? Well, make an experiment in your mind. Just think that you print every result which the computer, this TNH2, computes in 1 second. So you print it, of course, in small font, and of course you use both sides of the paper, and you print 1 page, another page, another page, another page, another page. How high would be the stack of paper which TNH2 produces in 1 second of calculation? Maybe it's difficult to imagine. The answer is 3.4 million kilometers, 9 times the distance to the moon. I don't want to say that you need a really fast printer to do this. That's of course nonsense. But my message is it's necessary to check the reliability of these results. Who can check these results? It's not possible to check the results, to print the results and check is this correct and are the calculations correct. That's not possible. Only the computer can check these results. So there should be additional tools built into the computer to check results. And these tools are, for example, valids and quires, which are defined in the Posit, in the upcoming Posit standard. So Posits, they have some advantages. They are a flexible trade-off between exponent and mantissa bits. You have the regime bits, which make it more flexible. And so for numbers which are close to 1, and probably if you correctly arrange your numbers, probably many numbers are close to 1. So if you calculate with numbers in the range 10 power 100, probably you did some error in your modeling. So in this case, if you are close to 1, you have a higher accuracy than in the IEEE standard. You have special representation for plus minus infinity, maybe one none, which one not a number, which or the same thing. So plus minus infinity is the none also. Yeah. So you have only one exception, that, as far as I understood that. So maybe I understood one of the talks in the morning incorrectly. So there is just one exception, namely infinity, and all other numbers, they are regular, and that of course that of course makes the whole structure much more regular. And there are quite a couple of applications in these papers where this additional accuracy is useful. But of course, these results are still unreliable. If we just use posits, we get posit results, floating point results. If we know the correct answer, we can compare and say with floating point we get 13 correct digits, with posits we get 14 correct digits. But if we don't have comparison or other tools to get the answer right, then we still do not know how good the results are. So valids are one tool for getting reliability. Valids, they are intervals with a lower bound and an upper bound. Both should be posits in our case. And of course, we can represent open intervals, closed intervals, half open intervals by using the U-bit of the posits. So there are several options how to represent this. So more or less we can represent any connected set of real numbers with, of course, with a finite number of bounds. We cannot represent any real number with it, but we can represent an enclosure of it. And this calculus is algebraically closed. That means if we do calculations, for example, a plus b, or a times b, or a divided by b, and so on, and most standard functions, they deliver another valid. So there are no exceptions. There are no things like not a number or not an interval or whatever. So every calculation delivers another valid. And this calculation is free of exceptions. Of course, the valid is somehow rounded outwards. We cannot represent the result exactly. We have to round outwards. But anyway, the result is another valid. Now, of course, interval arithmetic has a bad reputation. That's a typical example. The intervals, if you do naive interval calculation, the bounds tend to explode. So after a couple of operations, you get the result. Your value is between minus infinity and plus infinity. And so you say, here, I knew that before, so I don't have to calculate. Typical example, we compute the range of a function, and here we have a very simple function, f of x equals to x minus x. Of course, the range is 0. The result is always 0. But if we do interval calculations, we replace the real value x by an interval capital X. And so if we do the interval calculation here in the interval extension of the function, we get the interval 0, 1, minus 0, 1, and that's the interval from minus 1 to plus 1. So even in this trivial example, we get a huge overestimation of the result. Of course, the result, the true result, is contained in the interval, but yeah, this is really a huge overestimation. We can subdivide the intervals. If we do such a subdivision, we can reduce the overestimation. We can do this several times and get smaller and smaller intervals, so we can get relatively accurate intervals, nearly to maximum precision, but of course at additional costs. We have additional costs and we have less efficiency, especially if we have a multidimensional problem, not just a simple problem like this one. So it's better to use valids not in all places. It's not a good idea to replace every real computation by valids, and it's better to do some transformations before you start to calculate, and you should avoid variables to occur more than once. If a variable occurs more than once in interval calculations, there is some independent choice of the value in the interval, and that always leads to overestimations. You should use better algorithms, we will see that, and yeah, Quires, or otherwise termed exact dot products, and how this can be combined. Okay, so a major part of the calculation can be done in floating point, and it's a good idea just to compute some remainders in interval arithmetic, not the values themselves. So that gives usually much better results. So exact dot products, or also coined Quires here in our context, they should compute such sums and products of sums of products. They should be computed exactly in an internal format and rounded only at the end. So this format should be, it should be possible to round this to the nearest value, and of course it should be possible to round it to an enclosing valid. That's of course very important, that you have this sum of products, and you round it to a valid, a low bound and an upper bound. So you have an enclosure of the true value. It's also very useful to have the internal format of this dot product stored exactly in some internal format. You do not have necessarily to read it out, but it's very sensible to have it stored internally. For example, if you want this result in a kind of double precision posit, then you can achieve this. You round it to S1. S1 is the rounded result of this exact result of the internal result S, and then you just do the subtraction S minus S1. You still have the exact value S internally, and you subtract S1 and round the result, and you get an S2. So you have some kind of double precision or quadruple precision, whatever you term it, and for that you need the internal result S for further processing. You should not just compute a dot product or a matrix product in one step and then forget everything, but you should be able to store upon this and to continue to work with these internal results. So there are lots of software and hardware solutions for Quires. We saw one in the morning. That was a very interesting talk for me, to compute several components, 8 by 8, 64 components of a matrix product simultaneously, only in 32-bit arithmetic, but anyway. There are many options. For example, a fixed point accumulator, that you store all intermediate values in a kind of fixed point format. You need a long format, and of course in that case you have maybe a problem with carries, and you have to know how to handle these. There are other options, There are other options, for example, a sum and remainder operation, which I already proposed half a century ago nearly in my PhD. Sorry, my voice is not very good today. In my PhD thesis in 78, and there are many more recent publications by, for example, Siegfried Rump from Hamburg in Germany. Yeah, one of these options can be symbolized by this kind of shelf, and the drawers, they symbolize the words which are affected by the dot product. We calculate the product of two floating point numbers. We want to add them, and of course here we can we can add this to 3 drawers of 64 bits each. So we need just 3 drawers, 3 adders, which represent the result. But of course there may be carries. In the morning we saw these carries can, for example, be handled by adding additional bits which catch the carry. This version says we have for each drawer we have kind of 2 lights or 2 bits, red and the white one, which stores the information that the drawer contains all zeros or all ones. And if it contains, for example, all zeros, and you subtract, you do a subtraction, then you just switch from all zeros to all ones. That's just switching of 2 bits. So you do not really have to access the words. You only have to access a couple of bits, and this bit handling can be done very efficiently in more or less 0 execution time in comparison with multiplication and floating point addition. Yeah, actually in the 1990s we already built a chip for this as a prototype. It was of course in the technology and for the Intel processors of that time, more than 20 years ago. It was meant as a demonstration of technology that it is possible to achieve this and to implement this with a relatively modest hardware requirement. There were, for example, last year I was on a conference, Arith24, a big arithmetic conference, and there was a presentation by Jack Koenig from Berkeley in the United States, who did quite a similar design to accelerate exact dot products or quires. That's a picture how dot products can be expressed differently with a completely different algorithm. Okay, of course, maybe I should not go into details to save some time. Maybe I just should mention that there are many more options how to compute this. Validated results for numerical algorithms. That's my last part of the talk. Classical numerical algorithms, they compute an approximation. Possibly they have an error estimation, but no rigorous bounds. What we want is a rigorous error bound or an interval which does contain the exact solution. So we want an algorithm which computes verified or validated bounds. It should prove the existence of the solution and possibly also the uniqueness of the solution. And this can be achieved using valids and quires. Yeah, just maybe a few examples to demonstrate this. For example, we want to evaluate a function f of x, and we want to prove that there is no zero of the function in the range between a and b. Yeah, that's not so easy if you want to do it by floating point. Here we have 1, 2, 3, 4, 5, 6, 7, 8. We have 8 evaluations, and of course if you have 8 evaluations, you do not know what happens in between. So, okay, you do not evaluate the function at 8 places, but maybe at 100 places, or 1,000 places, or 1,000,000 places, but that does not change the principal problem. Still, it could happen that between 2 of your evaluations, 2 of your places, the function could look like this. It could escape and cut the horizontal line. You do not know. That's different if you use interval computations, if you use valids. In that case, you can check which of the intervals may contain zeros and which may not contain zeros. If you evaluate the function, use it valid arithmetic, then for example in this interval here from this point on the x-axis to this point on the x-axis, there can be no zero of the function. This is a mathematical proof, like in pure mathematics. There can be no zero. Or in this interval there may be a zero, we do not know. In this interval there may be a zero, we do not know. In this interval there may be no zero. So we can exclude a lot of intervals, and we have to study other intervals more precisely, for example by subdividing and or doing maybe higher precision arithmetic or whatever. This is an algorithm which can prove that there are zeros in certain intervals, that there may be zeros in certain intervals, but there may be no zeros. It is proved that there are no zeros in the other intervals. This idea can be used for global optimization, and that in fact gives quite fast algorithms, because usually people say interval arithmetic has an overhead. It's slower than usual floating point arithmetic, but that's not always the case, because using these ideas in global optimization, you can throw away many of the sub-intervals and say, I don't have to look further in this range. The optimum which I'm looking for can only be in this interval, maybe in this interval, maybe in a third interval, and I have to study these further, but I do not have to study many other intervals. So you can throw away maybe very quickly 99% of your range, and like that you can maybe even speed up the algorithm considerably. Oh, sorry. This is the interval Newton method. It works like follows. You have a starting interval x. It goes from here to here. That's your starting interval. And from this starting interval, you compute a new interval n of x. That's this interval n of x. How do you compute it? You do not use interval operations for all operations, but you choose some real number x, or floating point number, or posit, in your interval from x1 to x2, for example the midpoint, but it doesn't have to be the midpoint necessarily. You do the evaluation of the function value at this point, and then you apply the slope not in this point, but the slope in the whole interval. You need an interval enclosure of the slope of all values in the whole interval. So therefore you have here this relatively wide band of slopes, and this wide band of slopes is intersected with the x-axis, and that gives you the new value n of x. And then you have several options which can occur. One option is that n of x and x have an empty intersection. If that is the case, this is a mathematical proof that there is no zero in the interval x. So that's a mathematical proof. If n of x is a subset of x, not like this, that they just overlap, but n of x is in reality maybe a subset of x, then this is a proof that f of x has exactly 1 zero in x. And if we have this general case, which we see here, then we do not yet know. We have to compute further. We do the intersection n of x intersected with x, and that's the new starting point, x prime, for example, with which we do the same algorithm again. So maybe after a couple of iterations we get the first or the second status that zero has been found or zero has not been found. Or if we have bad luck, maybe after 10, 20 steps we still do not know what happens. In that case, maybe we have to use a different algorithm. A linear system solver. We want to solve a linear system ax equals b for real numbers or posits, whatever. It has an exact solution, that's a real vector x star, which of course we do not know. So how do we calculate this? How can we approach this? There are many options, but here first variant, we do an approximate inverse of r. no valids, just a posit calculation. We just have an approximation, which may be good or bad, we don't know. So we have an approximate solution, x tilde, for example, using this inverse. And now we want to check if the inverse and if the solution x tilde is good or bad. For that we calculate the error x star minus x tilde. Okay, we cannot calculate it because we do not know the exact solution x star. But starting with this concept, with E, this error description, we can compute a residual, R equals B minus A times x tilde, the approximate solution. And we can calculate a sequence of terms of vectors EI in this way. I forgot to mention the starting value. The starting value is just the approximate inverse times the residual. And in these calculations, it's extremely important that we should not use conventional floating point arithmetic or posit arithmetic or whatever. But here it is very important that we use valids and quires. Because here, for example, if you look at this term, b minus a times x tilde should be an approximation of the solution. So a times x tilde should be approximately equal to b. And so here we calculate something like b minus something which is very close to b. And if you do that in floating point arithmetic, you get more or less random numbers. If x tilde is a good approximation, then maybe r is a random number. So that, if it's a very good solution or a very good approximation, maybe r is 0. That would be fine, but otherwise we get just some random noise. So this calculation has to be executed with quires, with exact dot products. And under some conditions, then we can compute that x tilde, our approximate solution, plus the interval enclosure EI, that contains the true solution. And we can prove that this is the case. So it might be surprising that we start with an approximation which is perfectly unsafe. It can be good or bad, we don't know. But nevertheless, after some iterations, we get a verified result in the sense of pure mathematics. We can prove in a mathematical way that the true result, the true unknown real number, real vector x star is contained in the interval x tilde plus, that's a posit vector, plus the valid vector EI. Yeah, how do we do this? We need some algorithm. I mean, I think it looks not so complicated. Maybe, I don't know how much time I have. 30. Oh, a minute left, yeah, okay. So maybe I just like to mention the right-hand side. So what arithmetic do we need here? We need an approximate inverse that uses posit arithmetic. That's maybe the major part of the work. And then we have an iteration, and the iteration algorithm that needs valids and quires for the accuracy, valids for safety, and quires for accuracy. So that's necessary. And if we then can prove this enclosure, then it proves that the solution has been found and is contained in the interval. Maybe just a last slide, how to interpret these results. If E is a subset of the interior of Y, that sounds very complicated, but in fact it's just a couple of comparisons with less than and greater than instead of less than and equal to, and so on. And so if this is the case, then we have proved, mathematically proved by computer, that A is not singular. The linear system has a unique solution, and the solution is contained in the vector x tilde plus E. If this is not the case after a couple of iterations, say after 10 iterations, then we need maybe better methods. Okay. You can also generalize this for other maybe mathematical problems, for example, for the evaluation of polynomials and expressions, for the computation of eigenvalues, and maybe I just should refer to Professor Cooley's book. Just one mention. He will celebrate his 85th birthday in May, and he is still very busy with publishing papers and books. Like you see, just a couple of years ago, he published a new version of his book. Yeah, and maybe just one last sentence. For doing all this, we need a programming environment which provides the arithmetic operations, and with which we can formulate the libraries which we need for our purposes. Okay, thank you very much.
So we have time for maybe one quick question.
This particular talk, Coolidge is really the grandfather of all of the stuff that gave rise to this arithmetic, and it's a very general system for taking any block of operations, plus, minus, times, divide, and guaranteeing the accuracy. That last part, which he had to unfortunately rush through, is something that was developed by the University of Karlsruhe, Coolidge and his students, and it's all ready to go. It's a huge block of software that does all this stuff automatically. It's just been waiting for a number system that includes the exact dot product, and Floatingpoint won't do it. They've been asked repeatedly to include this, and they will not do it. And the interval, there's even an IEEE standard for intervals, and they rejected the exact dot product, guaranteeing that intervals will always be doomed to expand and get looser and looser results. You put the exact dot product back in there, and you can rescue interval arithmetic, and that's what we need to do.
Mm-hmm. Yeah, I just can agree to what you say.
Thank you very much.
Okay.
Thanks. Thank you.